Hello, I am Dr. Goodluck Ofebu, Geological Engineering Specialist at GNO Modeling Research, located in San Antonio, Texas, in the United States. The purpose of this presentation is to describe a new approach for modeling processes in geologic media. In the new approach, individual fractures and their behavior are modeled explicitly. However, the modeling is done in a continuum framework. The modeling approach is referred to as fracture-based continuum modeling with the acronym FBCM. FBCM offers a great advantage in modeling geologic processes because it combines the ease of continuum modeling with the accuracy of modeling individual fractures explicitly. The presentation starts with a description of FBCM as fracture-based continuum modeling for modeling mechanical and hydrological processes in geologic media. Then we describe examples of numerical simulations that we have conducted using FBCM. We will describe examples from hydraulic fracturing, an example from geotechnical analysis of foundations. Additionally, we will provide reference to examples of numerical simulations of basic laboratory test cases in our previous publications. The basic FBCM model is a continuum model of the domain. The model domain is discretized into continuum elements. We understand that a domain element is simply a subvolume of the domain. If there are pre-existing fractures, then the pre-existing fractures are discretized into planar segments based on their intersections with the domain elements. New fractures are generated in planar segments based on mechanical conditions in the domain elements. That is, the mechanical conditions in a domain element determine whether new fractures occur in the element. The model domain consists of fully connected continuum elements. Individual fractures are modeled explicitly as piecewise planar. Each domain element can host up to 6 fracture segments, that is, up to 4 segments of pre-existing fractures and up to 2 segments of new fractures. Each fracture segment intersects the element centroid and terminates on 4 element faces. Each fracture segment has a constant dip direction, and aperture. The aperture of a fracture segment may vary with time through the analysis. The dip direction, and aperture of segments of a fracture may vary among the domain elements. Each fracture segment is represented mathematically as a local transformation matrix. The fracture transformation matrix is used to calculate the behavior of the fracture segment as part of the behavior of the host element. The host element conveys fracture behavior to neighboring elements through hydromechanical interactions. In hydrological analysis, the fracture transformation matrix is also used to calculate fracture to element phase connection matrices for calculating hydrological interactions. The mechanical conditions of a domain element determine fracture initiation and deformation. A new fracture may initiate as a shear fracture or a tensile fracture, depending on the mechanical conditions at the time of initiation. An existing fracture segment may deform in slip mode or opening mode, irrespective of whether the segment is a pre-existing fracture or a new fracture. In FBCM modeling, fracture aperture is initiated with the fracture and updated incrementally during the analysis. There is no model prescription for fracture tip phenomena, fracture propagation, and fracture coalescence, because these are all controlled through hydromechanical interactions among the domain elements. Hydromechanical relationships are enforced through a piecewise tensorial aggregation of the behavior of individual fracture segments and unfractured matter. Next, let us describe an FBCM numerical simulation of hydraulic fracturing in previously unfractured sandstone. The domain model for the simulation was a rectangular block 80 meters by 80 meters laterally and a vertical thickness of 40 meters. The model includes a vertical well centered laterally. The middle 20 meters of the well was pressurized by fluid injection. The injection rate was varied in 4 stages to a total injection time of 150 minutes. We will next present the results, which show a central interior zone of fractured rock after 150 minutes. The 3 plots show the calculated fracture zone, which forms a cylindrical zone around the well. The axis of the cylindrical fracture zone coincides with the pressurized section of the well. The radius of the fracture zone is greatest in the middle and decreases upward and downward. Unfractured rock was excluded from the plots to make the fractured interior visible. Plot A shows the fractured elements. Plot B shows the dip of the fractures. Plot C shows the dip directions. All the fractures are vertical radial planes. These plots show the zone of fractured rock from numerically simulated hydraulic fracturing due to water injection in a single well in rock with one set of pre-existing fractures of 30 degrees deep, 210 degrees deep direction. Plot A shows elements with induced fractures, tension reactivated pre-existing fractures, or both. Plot B shows elements with induced fractures only. Plot C shows elements with reactivated pre-existing fractures. Unfractured rock is excluded from the plots to visualize the fractured interior. We understand that in this context, unfractured rock means rock with no new or reactivated fractures. The results indicate that the stimulation zone developed along strike of the pre-existing fractures. The next example shows using FBCM to assess the behavior of shallow footings at the top of a slope. The foundation setback from the slope crest was varied to develop several foundation designs. A full-scale load test was performed on each design using FBCM numerical simulation. The test results were used to characterize mechanical damage of the subsurface materials in terms of the occurrence of shear and tensile fractures. Also, the results were used to characterize the bearing capacity based on damage. The plots show key results from simulated full-scale load tests on shallow footings at the top of a slope. The figure on the left shows several plots of bearing pressure versus settlement from foundations of various setback, showing that the ultimate bearing pressure decreases with setback. The figure on the right shows the number of elements with fractures plotted against settlement for the foundation design with setback of 18 meters. The threshold settlement for damage occurrence is the settlement at which the number of fractured elements begins to depart from the initial condition. The threshold settlement is used with the information on the left figure to determine a damage-based bearing capacity. That is, the greatest bearing pressure that is too small to cause mechanical damage of the subsurface materials. The ultimate bearing pressure is the peak of the bearing pressure versus settlement results and can be determined directly from the analysis results. The plots described as bearing capacity were determined by applying the threshold settlement to the bearing pressure versus settlement results. The threshold settlement is a key parameter in the evaluation of the damage-based bearing capacity and is determined using the damage characterization. This FBCM load test of a shallow footing introduces the concept of damage-based bearing capacity and shows how to determine its value. To summarize, we describe the capabilities of FBCM. FBCM models discrete fractures and fracturing explicitly in continuum analysis, performs fracture initiation, deformation, propagation, and coalescence without remeshing. New and pre-existing fractures are modeled as piecewise planar. The deep direction and the initial aperture of a new fracture are based on the mechanical conditions when the fracture is generated. FBCM updates the aperture of new and pre-existing fractures as the fracture deforms. FBCM uses the fracture transformation matrix to calculate fracture properties and behavior. Also, FBCM uses the fracture transformation matrix to calculate the connection matrices for fluid flow modeling. FBCM has been implemented in computer codes CAMFRAC for geomechanics and CAMFRAC ENV for geohydrology. Thank you for listening to the FBCM presentation. GNO modeling research can be reached by email or phone.